Okay, Assalamualaikum and greetings everyone. Welcome back to another one of my video. So today I will teach you all about the lecture 5, which is about the damped oscillation here. So before we go through more about the damped oscillation, I will introduce you to some of the important importance components that is involved in the damped oscillation, which is what we call it as the complex number. Okay, complex number. Complex number is actually the component that is mostly like to use in the damped oscillation. Okay, so when we talk about the complex number, there are four main facts about complex number, which is the first fact is about I, which is also called as the imaginary number, which is equal to square root of -1. Okay, and at the same time I square is equal to square root of -1 power of 2. And when we do some multiplication between them, we will get that I square is equal to -1. So this one here is really important, and they are most likely to be seen in the damped oscillation. Okay. Now, the second fact is that we have a standard form of the complex number. Okay, the standard form, which is zeta is equal to A plus BI. This is what we call the standard form of the complex number, where A here, A is the real number, and at the same time it is also the real image of the Z. Okay, and B is the imaginary number, which is the image of the zeta. Okay, I will not explain more about the real image of the real of the Z, the zeta, and image of the zeta, because it is not that important. Okay, so if you want to know more about in depth about the standard form of this, yes, you should search some of the internet. But for me, it is not important. So let's get through here. The third fact is about the conjugate. Okay, conjugate of complex. The conjugate means that the opposite of standard form. Right? So this is what it means, the opposite of standard form of the complex number. Since we have the zeta is equal to A plus BI, that means for the opposite we have zeta star. Okay, zeta star here. Zeta star is equal to A minus BI. Here we have zeta is equal to A plus BI, but here we have the conjugate of its form, which is zeta star is equal to A minus BI. This is what we call the conjugate of complex, or the conjugate of standard form. Okay. Now when we talk about the conjugate, okay, here there are actually four form of conjugate, but here I will talk about two only. Two component of conjugate here. The usage between the usage between conjugate and standard form. Why do we have the conjugate here? Because we want to do some of the easier solution that we can obtain a real number. Okay, so here we have the first one, which is the sum of complex and its conjugate. Okay, which is zeta plus zeta star here, and what we get at is equal to alpha plus, sorry, a plus bi minus, plus a minus bi. Right? And what happens here, we can see that bi can cancel each other here. Now what we obtain that, it is 2a. This one is really important when it comes to proving the solution of the damper oscillation equation. Okay, and the second one is what we call as the subtraction of complex and its conjugate, which is zeta minus zeta star is equal to a plus bei, right, minus with its conjugate, which is alpha minus a plus bi. And as we can see that a can cancel each other, and we get that finally, which is 2bi. Okay, it's simple, right? Yeah, so far so simple. I think everyone can understand this. Okay, subtraction and sum. Right? So here is important here. And we go for the last one, which is we have the complex exponential function. The last fact, which is called as the complex exponential function. Okay, which is ei theta is equal to cos theta plus I sin theta. Okay, this is what it is. Now when it comes, as you can see here, okay, there is actually related to the standard form of the complex number here. As you can see here, right, this one is equal to z, and here we have the cos theta represented as the real image, real of the zeta, which is a, and then we have a, and then sin theta is the b, and I is the imaginary c. We have the standard form, but here we called it as the complex exponential function, which is represented as the same as the standard form of the complex number here. And now when you have the complex exponential function here, which is represented as the standard form, of course there is another relation, which is what we call as the conjugate, right? We have the conjugate. So conjugate of exponential function. So since we have the zeta here is equal to exponential power of I theta, so of course we have the zeta star is equal to a minus bi, right? So as I say that this is actually the opposite of the standard form, which is, see, we have the e power of I theta right now, so the zeta star should be exponential power of negative I theta. Right, simple, right? So equal to alpha, which is cos theta, and then minus with I sin theta. Right, pretty simple. Now we have the conjugate and its we have the standard form and its conjugate, right? Now when we have both of these, we can do what we call as the component to be used for the sum and then the subtraction, right? So here we have the sum. So the sum is zeta plus zeta star, which is equal to 2 alpha, right? So which means that e I theta plus e power of I negative I theta, which is we get that 2 alpha. What is 2 alpha? 2 alpha means that 2 times cos theta. 2 cos theta. This is really important to be used here. Okay, and then we have the subtraction. What do we get up when we subtract subtract with its between the standard form and its conjugate? Okay, so from the subtraction we get that zeta minus zeta star is equal to 2bi here, 2bi. And finally we get that e power of I theta minus its conjugate, which is e power of negative I theta. This is equal to 2, and then b is actually sine theta here, right? So it is 2i sine theta. It's very important here. Okay, please take note about this. Okay. Now that's simple, right? Okay, now when it comes to this form here, the scientist has an idea to relate it into the SHM, into the simple harmonic motion, which is, we know that the equation of the simple harmonic motion, equation of displacement, right, which is in SHM, right, it is actually XE is equal to E sine omega t plus pi naught, right? If you remember this, I hope so you remember this. Okay, this is the general form of the displacement in simple harmonic motion here, right? So here, as you can see, we have this one right here, the sine omega t plus pi naught here. This one has its own trigonometry identities, which is related to sine A plus B, where A is omega t and B is pi naught, right? So I will do some refreshment here, some of the reminder here. So sine A plus B is equal to sine A cos B plus cos A sine B, right? This is what we call the trigonometry identities that we should be applied here, right? So when we jump back into here, we get that xt is equal to A times with the sine A, which is sine omega t, sine omega t, and then cos B, which is pi naught, right, pi naught, and then plus with the cos A, which is cos omega t sine pi naught, right? So here we want to in this here I want to show you that what do I call that? I want to show you that this one and this one can be substitute from the exponential complex function here. Okay, first I will do some of the what we call it, the factorization. Okay, so xt is equal to, I will put out the a here, so a cos pi naught, okay, and then multiply with sine omega t, and then plus with the a sine naught, okay, a sine naught, pi naught, sorry, and then multiply with cos omega t, right? Very simple, right? Okay, now let's say that I want to do some of the what we call it as the substitution. Okay, let's go back to here. Okay, let's go back to here. This is the idea to do some of the substitution. Okay, so here we have the 2 cos theta. Okay, 2 cos theta. Let's say that theta is equal to I omega. Okay, so when we do that, we get that when we do some substitution here. Okay, we get that e I omega t plus exponential power of negative I omega t is equal to 2 cos omega t, right? So here we want to show you what is the form for cos omega t. So we bring down the 2 to the left side, we get that 1 over 2 e power of I omega t plus exponential power of negative I omega t, which is equal to cos omega t. Okay, let's log on for this one now. Okay, let's log on. Okay, now let's move on to here. This one has relation to sine omega t, right? So let's substitute omega t, let's substitute theta with I omega. So we get that e power of I omega t, right? Is we substitute theta with omega t, and then minus e power of negative I omega t is equal to 2I sine omega t. Okay. Now we bring 2I to the left, to the left side. We get that 1 over 2I multiplied with exponential power of I omega t minus exponential power of negative I omega t, and we get that sine omega t. So notice that here we have the imaginary number on the denominator. We cannot put imaginary number in the denominator because when it comes to creating calculator, when we do some calculation in the calculation, okay, in the calculator, we get that it is actually a math error. We cannot 1 over negative square root. We cannot do 1 over 2 multiplied with negative 1. Okay, when we do some square root of negative 1, which is I right here, we will get that it's a math error. There is no solution for this one. So we want to remove 2I by doing some conjugate, okay? Do some conjugate, okay. How do we remove 2I from each denominator? What we do, we will do some of the multiplication here. Multiplication with its conjugate. Now go back here. So we know that we have the complex here. Complex standard form. I say I do the SF here, which is 2I, right? So 2I, this is A plus BI, right? It's like 0 plus 2I here, right? And we have the conjugate, which is A minus BI, right? Which is 0 minus 2I. Okay, now since that we have 1 over 2I, okay, we want to do some change here, okay? 2I, which is meant 1 over A plus BI, okay? So here we want to do some the multiplication of its conjugate, which is 1 over 2I times with the itself, okay? But here we will do multiplication with its conjugate, okay, which is negative 2I, and here is also negative 2I. This is what we call multiplication with its conjugate, okay, which is here, okay. So what we get is finally we have negative 2I up here, and the denominator is equal to negative 4I square, right? 2I multiplied with negative 2I, we get that negative 4I square. Okay, now we can cancel out the subtraction here, and we have the I square. We know that I square is equal to negative 1. This is negative 1. So finally we get that 2I over 4 times with negative 1. And here we can remove out the 2 here and 4, which is here like this. And finally we get that it is equal to I over negative 2. This is what we will get. Okay, now we go back here. This one will equal to negative I over 2 e power of I omega t minus exponential power of negative I omega t, which is equal to sine omega t. Let's look for this one. Okay, now we do some substitution inside this bag, right? So we do some substitution. Xt is equal to a cos I naught. Okay, and then sine omega t, which is equal to negative I over 2 multiplied with exponential power of I omega t minus exponential power of negative I omega t. So multiply with negative I over 2 multiply with exponential power of I omega t minus exponential power of negative I omega t. Right? Right, and then plus with the a sine I naught multiply with cos omega t, which is 1 over 2 here. Okay, 1 over 2, 1 over 2 exponential power of I omega t plus exponential power of negative I omega t right here. Okay, now we can do some straight multiplication here, which is xe is equal to a dot multiplied with negative I over 2. We will get that negative I a over 2, okay, cos I naught, and then times with the exponential power of I omega t minus exponential negative I over omega t. And then here we have here a times with over 2, 1 over 2, which is a over 2 sine I naught, and then times with the exponential power of negative I omega, exponential power of I omega t plus exponential power of negative I omega t. And here we can do what's called is as the factorization from here and here. If we sort it out, finally we get that xt is equal to negative I a over 2 cos I naught, okay, and then hold on, let me check that equation. Okay, this is negative I omega a over 2 cos pi naught. Okay, and then I want to relate, which is the same as this one. Okay, see, we have here, and then we have here plus, okay, plus a over 2 sine pi naught multiply with exponential power of I omega t. Right, we extract this one first, and then we go on to the next one, which is plus I multiply with a over 2 cos pi naught, okay, and then plus with the a over 2 sine pi naught, and then power multiply with negative exponential negative I omega t. Okay, here is the final form. It's okay if you still blur, you have to look at it slowly. Look slowly, okay. Right. From here, okay, this is where the new constant form. Okay, the new constant form, which is that this one right here, from the lecture note, this one, okay, this one right here will represent as the beta, this one, and this one right here represent as the conjugate of beta, which is beta star. Okay, so as you can see, we have here, we have the form like this one. Okay, this is the final form, which is this one is when we do some of the extensions here, we have here is as a A, okay, and here is the B. So from here we have that beta is equal to A and then minus BI. Alright, minus BI, and beta is equal to A over 2 sine I naught minus with I times with A over 2 cos I naught. Alright, this is the form of beta. This jot down here, and we have the its conjugate. When it's minus, then there is plus here, right? So beta star, which is written as alpha plus bi. Okay, and then finally beta star is equal to A over 2 sine I naught, and then plus with I times A over 2 cos I. Okay, this one is really important. This one we will use it at the end of the topic. Yeah. Alright, now clear, right? Alright, good. Now, okay, hold on. We need to take a breath. Now I'll go to the next page here. Now, see we have the xt. Alright, xt is equal to, I'll copy back here, which is negative I multiply and yada 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 here. Okay. Sorry. Negative I times A over 2 cos I naught. Okay, and then plus with A over 2 sine I naught, and then plus exponential power of I omega t plus with the I times A over 2 cos I naught minus with the, so is it minus? Yeah, it should be plus. It's plus A sine A over 2, sine pi. Okay. Now I will do some exchange here so that you can see how clear is it. So xt is equal to, I'll put the imaginary form to the right side and the real on the left side here, which is A over 2 sine pi naught, okay, minus with I times A over 2 cos pi naught, exponential power of I omega t plus A over 2 sine pi naught plus I times with the A over 2 cos pi, and then exponential power of negative I omega t. So as I said that this one, okay, this one from here is equal to beta, right? Beta. So this one is beta, this is beta, and this one is its conjugate, which is beta star. So finally we get that xt is equal to beta exponential power of I omega t, and then plus with beta star exponential power of multiply with exponential power of negative I omega. Okay, so now we want to do what we call as more easier, which is we form another constant. Okay, this is the first constant we see here, which is beta, and there's another constant which they said that alpha is equal to I omega. They want to do what we call as another form, which is another easier form. Okay, so xt is equal to beta exponential, and then I alpha becomes alpha e, and then plus with its conjugate beta star and exponential power of negative alpha t. Okay, this is the final form here. Okay, this one will be useful. Okay, now we want to do some of the derivative of exponential function. Okay, so here we have the beta exponential power of a alpha plus t plus beta star multiplied with exponential power of negative alpha plus t. Okay, we can from here we can do some of the derivative of this function with the respect of t, because we have the variable of t here that which we can use to differentiate. Okay, so what happened here, we want to use that let let u equal to beta e with the power of alpha t, or beta star with the exponential power of negative alpha t. We want to do here, this is what we call, we want to do some of the derivatives of exponential function. Okay, which is here. Okay, now we want to do some of the derivative. Why? Because right now this is displacement, right? Now how do we calculate? How do we form an equation to find acceleration or velocity? Which is we have to relate with the derivative. Which is now this is the first order. This is the displacement. Now we want to find the displacement. Velocity, which is rate of change of displacement. This is velocity x single dot at the time t, and finally we get that we have to integrate this form. Okay, we have to differentiate this form, both of this form. Okay, now we have the here to differentiate this, we have to use the what we call it as the chain rule. Okay, chain rule. So I'll go back to chain rule. Okay, we have here dy dx is equal to dy over du here. So dx. Du dx, and here du. Okay, so here let's say we know that u is equal to beta e multiplied with alpha t. Okay, we have this form right here. Okay, and then hold on. Okay, we have to form another one. Okay. Don't look at this one. Okay, this one we change this one as the dx over dt, right? We want to find dx over dt. Okay, and that's equal to dx over dt here, and then du. Here is the problem. Okay, let's say that beta u. Okay, this is okay. Let's just forget this one. Okay, so we have the beta e multiplied power of alpha t, right? Here. Okay, to find u, okay, u is unit. U is here, the power. So we want to say that u is equal to alpha t, and when we differentiate u with the respect of time, we will get that we will get only alpha, right? Alpha right here. Okay, now dx over du, okay, which is this is du over dt. Okay, so we see that u is equal to alpha t. So dx, so let's say x is equal to beta exponential power of alpha t. So we want to find dx over du. Okay, which is equal to, from here we cannot integrate anything, right? So it will stay the form as the same one, which is beta exponential power of alpha t. Okay, now we do some substitution here. Okay, so you see that dx over dt is equal to du dx over du, which is beta, okay, beta exponential power of alpha t, and then times with the du over dt, which is alpha. And finally we get that it is equal to alpha beta e power of alpha t. Okay. Now let's move on here. So alpha beta e power of alpha t. And we know that beta exponential power of alpha t is equal to u, right? ut, because of t. Okay. So finally we get that alpha u in respect of t. Alright. Now let's look at the second order differentiation, which is the rate of change of velocity, which is x double dot, right? Which is acceleration, right here. So we have to do another chain rule to do some to get the x double dot here, to get the second order differentiation of the displacement here. Okay, so we still use the same rule, okay, which is I'll use this rule, okay, this here, because we have formed another formula. Okay, so we have this is the first, this is the second. Okay, so we have dx over dt equal to dx over du, okay, times with the du over dt. Okay, so we know that u is alpha t, right? Alpha t here. Okay, alpha t. And so when we differentiate it with respect of time, we get that it's equal to alpha here. And now we go to the x. So let x is equal to sorry, this should be stop. So we have x dot, which is equal to alpha beta e times alpha t here. So we have alpha b and then exponential power of alpha t here. Alright. Now I'll skip the row, I'll skip it, okay, I will skip it. So we get that delta x single dot over du equal to alpha times beta e alpha t. So beta exponential power of alpha t. From here we will always get the same form when it comes to delta x single dot with respect of u. It is always the same form here. Okay, pretty simple, right? Okay, now let's look at the what we call as the different substitution. Okay, so we know that dx single dot over dt is equal to dx dot over du times du over dt. So only do some substitution inside here. So we get that dx single dot over du, which is equal to alpha beta exponential power of alpha t, and then times with the du over dt, which is equal to alpha. And finally we get that alpha square beta e power of alpha t. And finally we know that beta e power of alpha t is equal to ut. So finally we get that alpha square u. Right? Very simple. Okay. And then the third derivative, I don't want to talk more about it. I'll just only explain these two here. So these two is what we learned before, right? What we learned, which is displacement, velocity, and acceleration. And the third derivative, I will not explain because it is not important. It is useless. Just don't look at it. Okay, now let's look on here. How do we find the displacement? How do we find the velocity when it comes in this expression? Okay, so we multiply dx over dt is equal to x single dot t. We will get that. I will do another chain rule. Okay, chain rule. Here we want to find dx over dt is equal to dx over dt, and here du and d. As usual, let u is equal to power of negative alpha t. U is negative alpha t, and when we differentiate u with respect of time, we get that it is equal to negative alpha. Okay, sorry about that. Now we want to find dx. So x is equal to beta exponential power of negative alpha t, and we want to differentiate with respect of u. Actually, we can differentiate this. We know that this one, negative alpha t is equal to u, right? So beta e power of u. Okay, so we can differentiate with respect of u. It is, since we have the exponential eu. Okay, I forgot to explain more of before here. We have the exponential eu. So when we differentiate, okay, let's say that we have ex. Okay, let's say that y is equal to e power of x. Okay, when we differentiate this, we still get the same. That's why I ignore. I just write it out because it is not that important to differentiate again, because it is still we still obtain the same form. Okay, so we get that it is equal to ex, same as this one. We have this one. Okay, so finally we get that it is the same, beta e u here, right here. Okay, so which is also equal to beta e negative alpha t, and then we can do some substitution here. So dx over dt is equal to dx over du, which is dx over du is equal to beta star. So this is star. Okay, beta star exponential power of negative alpha t, and then times which is du over dt, which is negative alpha, and finally we get that dx over dt is equal to negative alpha beta e power of negative alpha t. Okay, now we do some substitution here. We get that it is equal to negative alpha beta star e star e power of negative alpha t, and it goes on after that. Okay, I think you understand, so I don't need to explain more. Okay, you know how to apply the chain rule. Okay, so here we will get the, when you master the chain rule, you can only just look at the equation, you can do it actually. So from here I can see that this one can be integrated, differentiated. So this one will equal to negative alpha times negative alpha, and then just put it back me beta star exponential power of negative alpha t, and finally add single dot with respect of time, alpha square beta star e power of negative alpha t. And at the end we will get that, so this is equal to negative alpha u, because u is equal to beta star e power of negative alpha t. So here at double dot here at the time t is equal to alpha square u t. So notice that we have the same acceleration as the left side here, except this one. This one is not. Okay, so here, okay, don't mind it. Okay, just like there's some of the fun facts here. You can see that both of these equations, when it's been differentiate 2 times, we get the same equation for the acceleration. So okay, now we're done to that about the introduction to the complex number. Now let's move on to exactly what we need to learn. Okay, this is just the introduction, because this introduction is important, because in damped oscillation we need to use more about this. We have to use more about this one, about all of these components we learned here. Okay, now let's move on to 4.2. Okay, I'm just gonna stop here, and I will continue in the next video. See ya.